are one in our mission and vision, instilling excellence in electrical profession, having a dynamic professional.
Hello, good day to everyone. Once again, this is Professor Roger Flores of Central Mindanao University, Muswan Bukidnon, Professor of the subject EE41, Electrical Circuits 1. Today, we are going to discuss Chapter 7 of our course EE41. It is entitled Analysis of Resistive Circuits with Controlled Sources. Here we are going to discuss the different solutions of any problem consisting of several sources. It is either voltage or electrical sources, or both voltage and electrical sources. Okay, so we have this Chapter 7, Analysis of Resistive Circuits with Controlled Sources. Okay, so to start with, we have this, our topic, our contents, sources conversion or source conversion, Melmans Turin, and number 3 is maximum power transfer Turin. Okay, to discuss about sources conversions, okay, so we have this simple circuit having a voltage source and internal resistance R sub S. So we have here R sub S here. Then we have this assumed R sub L, or the load resistance with the load current here. Okay. So all sources, whether they are voltage or current, or both voltage and current, have some internal resistance in the relative positions shown below. So we have here. Okay, so it is important to realize that sources conversions are equivalent only at their external terminals. So in this circuit here, these are our terminals, no? Okay, so these are our terminals for the load resistance R sub L. So the equation of the current I sub L is equal to the source voltage E, or the EMF, divided by the total resistance. Our total resistance here is the sum of R sub S and R sub L. Okay, so we have this R sub S plus R sub L because it seems that they are connected in series. Okay, so to simplify or to convert this this internal circuit here with the source voltage of E to its equivalent source voltage of I. So we have this solution here, no? If we multiply this equation here of I sub L and by a factor of 1, which we can choose to be R sub S divided by R sub S, so meaning to say that this is just equal to factor of 1, and then it does not alter our equation here, no? So our 1 here is R sub S divided by R sub S, so we have here. Then if we are going to combine E over R sub S, so we have this E over R sub S. This will be multiplied by this remaining R sub S here. Then we have that divided by R sub S plus R sub L. Now take note that from Ohm's law, our voltage divided by the resistance is equal to our current I. No? So we have this R sub S times I divided by R sub S plus R sub L. Now, therefore, if we are going to look at the equation, this is it seems that in our previous chapter discussing about the current divider rule. Okay, so it seems that your I here is your total current, your I, the total current. Okay, divide by the opposite, which is your R sub S. Okay, so we have this R sub S divided by the sum of these two resistances. Okay, so the the circuit now, the equivalent circuit of the voltage source is equal to this current source, in which your current here is equal to E over R sub S, and your it is now our current source is parallel with your parallel with your uh, internal resistance. Okay, so let us have this example one. No, so based on this circuit here, having the internal resistance of 2 ohms, then we have the load resistance of 4 ohms, then our AMF, our source voltage is we have this 6 volts. No? So from that, our letter A requirement, okay, so we have this convert the voltage source of the figure to a current source and calculate the current through the 4 ohm load for its source. So you're going to determine the current using the voltage source of 6 volts, and or determine the current through the load using that equivalent current source. No? Then letter B, replace the 4 ohm load with 1 kilo ohm load and calculate the current I sub L for the voltage source. Okay, letter C, repeat the calculation of part or letter B, assuming that the voltage source is ideal. Now, meaning to say ideal is the internal resistance is equal to 0 ohm. Okay, then because R sub L is so much larger than R sub S, is this one of those solutions where assuming that the source is ideal is an appropriate approximation. Okay, so that is our example number one. So, as you can see here in our solution, so you have this circuit of the given circuit, no? The internal resistance is 2 ohms, the source voltage is 6 volts, the load resistance is 4 ohms. Then, using the formula of I is equal to the Ohm's formula of Ohm's law, I is equal to E over R sub S. Your source current, your current here is equivalent to 3 amperes, because that is equal to 6 volts divided by 2 ohms, then that is equal to 3 amperes. So that is your current source equivalent in the equivalent source current here. Okay, so that is the same current that will flow here. Okay, so it will become the total current of this resistor connected in parallel, the R sub S and the load current of R sub L. Okay, so to solve for using the original circuit, no, using the original circuit, the I sub L, this current here, is equal to the source voltage divided by the sum of these two resistances, the internal resistance of the source and the load resistance R sub L. that is equal to 1 ampere. Then by using this equivalent current source circuit, okay, from the formula of R sub S, the internal resistance of 2 ohms times the current, okay, source current divided by the sum of these two, no, the R sub S and R sub L. So we have this 2 times 2 ohms times 3 amperes divided by 2 ohms plus 4 ohms. That is also equal to 1. So it is either it is source current with its equivalent, or the original source current, what was this one, the EMF of 6 volts with its equivalent current source. Then they have the same load current of 1 ampere. Okay, so just to continue, for letter B, uh, assume that the load resistance is changed to 1 kilo ohm. So you have this 6 volts divided by 2 ohms. Okay, 2 ohms, our internal resistance, plus 1 kilo ohm, our load resistance, because we change our load from 4 ohms to 1 kilo ohm. That is approximately equal to 5.99 amperes. Okay. So by using the Ohm's law, which your I sub L, now according to the problem letter C, your I sub L is equal to the voltage divided by R sub L. Okay. Then we assume that our circuit is ideal, so therefore no internal resistance. Then if you're going to divide using Ohm's law with the ideal circuit of internal resistance equal to 0, that is 6 volts divided by 1 kilo ohm. So it is approximately equal to 6 milliamperes, or more or less very near to 5.99 milliamperes. So the reason there is that our R sub L is very much greater than R sub S. So it seems that because our internal load resistance is very much higher than the internal resistance, then it seems that there will be no effect. No, so that is why most of the time our internal resistance is neglected, because it has a very big difference with respect to the internal resistance. Okay? Okay, so this time let us discuss the Millman's Theorem. Okay, so this Millman's Theorem is applicable if we have uh, voltage sources connected in parallel. Okay, so the application is that any number of parallel voltage sources can be reduced to one source. No, so as you can see here in our circuit, we have three voltage sources. We have E sub 1, E sub 2, and E sub 3. So we have three voltage sources with the respective internal resistance of R1 for voltage source 1, R2 for voltage source 2, and R3 for voltage source 3. So we have, let us assume that we have this load resistance of R sub L. So Millman's theorem will help us how to simplify or how to combine these voltages, these three voltages, and how to combine these resistances with, of course, so as you can see here, our voltage sources here is reduced into only one voltage source. Okay, so we have these three steps, no? And step one is convert all voltage sources to current, okay, or current sources. Now, as we know, our current sources, or for example, for current I sub 1, it is just the uh, result or the quotient of according to Ohm's law, it is A sub 1 divided by R sub 1. Or as we know that uh, 1 over R sub 1 is equal to conductance, which is equal to G sub 1. So meaning to say that your current I sub 1 is either it is equal to E sub 1 times G sub 1, the conductance, or E sub 1 divided by R sub 1. Because as we know that I will repeat that your 1 over R sub 1 is equal to G sub 1, which is your conductance. So your conductance here, so we have this G sub 1 here, no? This is for the voltage source 1. For voltage source 2, we have this converted to current source. So we have this I sub 2. Then it is equal to either E sub 2 times G sub 2 divide, or it is equal to E sub 2 over R sub 2. So similarly, we have this voltage source 3 here. It is E sub 3, or this is your current source I sub 3. This is E sub 3 times G sub 3, the conductance, the internal conductance of your voltage source 3. Or that is equal to E sub 3 divided by R sub 3. So this is your G sub 3, the conductance, the internal conductance of our voltage source 3. Okay, so this is the first step. No? Convert all voltage sources to its equivalent current sources. Okay, step number 2, combine parallel current sources and the conductances. No? So, according to Kirchhoff's current law, summation of currents in any junction, okay, so that is equivalent to your total current. So you have here your total current is equal to I sub 1 plus I sub 2 plus I sub 3. Because they are connected in parallel, current of individual sources is being summed up, no? So being added. Okay, so with regards to the conductances, so since we have this one, no? So our total conductance is just simply equal to G sub 1 plus G sub 2 plus uh, G sub 3. That is your total conductances. Or the 1 over total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So anyway, that is for resistance, and this equation here is for conductance. So therefore, your total conductance is equal to G sub 1, G sub 2 plus G sub 3. We have this circuit here. Okay? And this circuit of the source current can be converted back to the voltage source. Okay. So for step number 3, convert the resulting current source to its equivalent voltage source, and the desired single source network is obtained. Okay. So this Melmans Turin states that for any number of parallel voltage sources, this is your equation. Okay, using Ohm's law or using the conductance, equivalent conductance. So the equivalent voltage source is equal to the total current divided by the total conductance. or that is simply equal to plus minus I sub 1 plus minus I sub 2 plus minus I sub 3 or plus minus I sub n. Why is that it is plus minus? Because it depends on the how our source is being connected, no? So being connected. So it is either additive or subtractive, no? So we have this divide by g sub 1, g sub 2, g sub 3 up to g sub n. So that is your total g sub t. Okay, so or um, it could be written this manner, no? It is plus minus e sub 1 times g sub 1, that is equivalent to I1 here, or plus minus e sub 2 g sub 2 plus minus g sub 3 times e sub 3, or up to e sub n times g sub n. So all over g sub 1, g sub 2, g sub 3 up to g sub n. Okay, so your equivalent resistance, of course, it is the reciprocal of the reciprocal of our g sub t, or it is simply equal to 1 over g sub 1 plus g sub 2 plus g sub 3. Okay, so that is our equation and our circuit. It has it is already reduced to the equivalent resistance and the equivalent voltage source. Okay, so from that equation, it is we have now this R equivalent is equal to this equation, and our your voltage equivalent is equal to this equation, and the R equivalent is equal to this equation. So we are familiar already with this one. Okay, so having this example number 2, using Melmans Turin, find the current through the voltage across the resistor R sub L. Okay, as you can see here, we have these three voltage sources, A sub 1, A sub 2, and A sub 3, with 10 volts, 16 volts, and 8 volts respectively. Then we have also the internal resistances of 5 ohms, 4 ohms, and 2 ohms respectively. So our load resistance is 3 ohms. Our problem here is to solve for I sub L and V sub L. Okay. So from the equation of the equivalent voltage, so we have this equation here. It has been given, and it is derived now. So we are going to substitute all the given. So like for example, the voltage here is 10 volts, so we have 10 volts here, and this is positive because we assume our current direction here. Then that is over 5 internal resistance of the voltage source 1. Now take note in voltage source 2, because the connection is uh, subtractive, no? So we have this, that is the reason why we have this minus here, no? Okay, so our current here is negative, because the direction now is from positive to negative. So we have this minus 16 volts divided by 4 ohms. So that is our current here, equivalent current. Then for the third source here is sub 3. We have our voltage is 8, and our internal resistance is 2 ohms, and it is positive because the flow of the current here is from negative to positive here. So our denominator is the sum of the reciprocal of the internal resistances. We have this 1 over 5 ohms, then we have 1 over 4 ohms, we have 1 over 2 ohms. So if you are going to substitute all these things here, simplify, Okay, so we have this E equivalent is 2.105 volts. That is the internal, oh, that is the equivalent voltage source. Okay, so we have that one. So the equivalent resistance is of course the sum, the reciprocal of the sum of the individual reciprocals of the individual resistances. So we have that 1.053 ohms if you are going to simplify all those things here. So that is 1 over 0.95 Siemens, or reciprocal of 0.95 is more or less equal to 1.053 ohms. Okay, so because of that, then the equivalent resistance is equal to 1.053 ohms here. Your equivalent voltage sources is 2.105 volts. So, according to our problem, we are going to solve for I sub L and V sub L, the load current and the load voltage, no? So the load current is now equal to um, the load current is equal to the source voltage of 2.105 divided by the sum of these two resistances connected in series. So that is why we have this 2.105 divided by 4.053. So that is simply equal to 0.519 amperes. Okay, so if you're going to determine the load voltage here, the load voltage drop here at the load resistance of 3 ohms, then you're going to modify Ohm's law. You have to multiply your load current and the load resistance, and that is equal to 1.557 volts. So that is our answer. Okay, so more or less we're able to apply Millman's Theorem, where we try to combine, we try to combine all voltage sources. Then out of these voltage sources connected in parallel, then we will be able to determine or compute the load current with equivalent load voltage drops in that specific circuit. Okay, so this time let us proceed to maximum power transfer theorem. Now, by the way, in the maximum power transfer theorem, we will make use of the Thevenin theorem, which we can be discussed in the next chapter. But anyway, I will give you some hints, some solution on how to apply this Thevenin's theorem, because this is applicable in this maximum power transfer. So, maximum power transfer, according to our definition, it states that a load will receive maximum power from a linear bilateral DC network when its total resistive value is exactly equal to the Thevenin resistance of the network assigned by the load. Okay, so the internal resistance is equivalent to the looking back resistance based as in the load side, no? The load side. So, for example, we have this. This is explained, no, in this circuit here, no. So we have the Thevenin voltage, we have the Thevenin resistance, the looking back resistance, and it is in series with our R sub L here. Then as you can see, your R sub L here is variable because whatever the value of your internal resistance, it is equal to the load resistance, no? Or simply your load resistance here is equal to the Thevenin resistance. So that is why this is variable. Okay, this condition of R sub L is equal to RTH or R sub TH is uh, we will be having our maximum power transfer to this load here. Or with the equivalent um, current source, or it is called Norton, no? Norton Turin, Norton Turin, no? So I sub n, the Norton current, you have this the Norton resistance and the load variable load resistance here. Okay. So anyway, in this condition, maximum power transfer, we try to discuss or we try to apply two theorems, Thevenin and Norton equivalent. Okay. Okay. So this is the solution to determine the maximum power transfer. No? So we have this your current, the load current is equal to the Thevenin voltage, then divide by the sum of the Thevenin resistance, the looking back resistance, and the load resistance. Okay, so your uh, power that could be delivered to the load is just uh, simply equal to the square of our current times R sub L. No? So that is the formula that the power is equal to I squared R. Okay, so this portion here E sub th squared all over the square of R sub th plus R sub L is your I sub your I, no, I squared, then multiplied by R sub L your resistance here, no, the load resistance. Okay, so similarly your okay, so we have this one, no. Similarly for our Norton, the Norton current and the Norton resistance, that is using that one. So we have this P sub L. The load power is equal to your I sub n R sub n. That is your E sub th equivalent as we defined in a previous discussion. So that we have that I sub n R sub L plus R sub n quantity squared times we have this R sub L here. So for the maximum power transfer, as we said that the internal or the load resistance is equal to the Thevenin resistance and the Norton resistance. So if you're going to use this equation here to have a to have maximum power transfer, then convert all resistances R sub L to R sub TH. Okay, so this will become R sub TH. This will become R sub TH. So what will happen? We have these two. This is R sub TH plus R sub TH is 2 R sub TH quantity squared. So that is equal to 4 times R sub TH squared. So the numerator here is R sub TH. One of the R sub TH we can be cancelled. So that is why we have this E sub TH squared divided by 4 R sub TH. Okay? So that is from here, we are going to apply maximum power transfer. And again, how? Then it is R sub L is equal to R sub TH. Similarly, from this equation here, okay, so convert R sub L to R sub N. So we have R sub L here, then this is R sub N. This R sub L here is R sub N, so we have now 2 R sub N. Then we have quantity squared, so we have this R sub L here is, we have R sub N here squared, and we have R sub N here. So we will be able to cancel this R sub N squared from the denominator here. So that is why we have this the equation for maximum power transfer using the Norton current. We have that I sub n squared times R sub n divided by 4. Okay, so let's continue with this next example. We have this example number 3. For the circuit of figure below, letter A, so we have this figure below here. As you can see, our circuit here is having two voltage source or two sources. It is the voltage source and a current source. Okay, so we have this R sub 1, maybe an internal resistance of the your voltage source 1 of 15 volts, and your R sub 2 here is the internal resistance of your current I sub, or your current 5 milliamperes, no? Okay, so our load here is of course variable, because your question, your our problem here is to determine the value of the load resistance required to ensure that the maximum power is transferred to the load. Okay, so we have to determine, no, the load resistance. First requirement is the load resistance, uh, so that to ensure that the power that could be transferred here in this load is okay, sorry. The load resistance is maximum, no? Now, letter B, find V sub L, I sub L, and P sub L, or the load voltage, the load current, and the load power when maximum power is delivered to this load. Okay, so what you're going to do first is to determine the uh, looking back resistance, or the Thevenin resistance, no? R sub TH, the Thevenin resistance. So in Thevenin Turin, to solve for the looking back resistance, eliminate all sources. Now, we have two sources. We have the voltage source and the current source. How you are going to eliminate the voltage source, for example, what you are going to do, replace this voltage source with a wire, short-circuiting these voltage sources. Okay, so as you can see here. Now, how you're going to eliminate the current source? Current source, take note this one. Current source is could be eliminated by just simply disconnect or removing your current source of 5 milliamperes. Okay, so we have this circuit now. So just to investigate, no? This portion here is short-circuited. This portion here is open-circuited. So what will happen to our two resistances of R1 and R2? They are now simply connected in parallel, no? So R sub 1 is in parallel to R sub 2. If you are going to determine the looking back resistance, or the resistance, the total resistance, starting from the load side, or terminal A and B here as we defined, then that is just the apply the solution of parallel circuits, two resistors connected in parallel. So therefore, your Thevenin resistance is just equal to the product of R sub 1 and R sub 2 divided by the sum of R sub 1 and R sub 2. So that is simply equal to 1.5 kilo ohms. That is the looking back resistance. Why is it called looking back resistance? Because that is the resistance seen from, or seen from the load side. Okay, so again, just to emphasize that to determine the looking back resistance, or the Thevenin resistance, is just simply remove all the sources. How to remove the voltage source, short circuit, and how to remove current source, then open circuit. Okay, so if you're going to open circuit this one and short circuit this, then your R sub 1 is in parallel with R sub 2. Okay, so simplify, then your Thevenin resistance is equal to 1.5 kilo ohms. Okay, so now as you can see here, okay, what you're going to do next is that since we have these two sources, the voltage and the current sources, I'm sorry. So you are going to solve for the Thevenin voltage, or which is your Thevenin voltage is the terminal voltage here, the terminal voltage V sub EB. Okay, so since we have two sources, voltage and current, then you are going to determine your terminal voltage here. Then later that will become your Thevenin voltage from this portion here going back, no? Then two sources, meaning you have more or less two value of your V sub EB or E sub TH later on, no? So why 2? Because you are going to determine this voltage V sub EB the, using first your source voltage and then another value of your V sub EB using next your current source. Okay, so again, if you're going to use the voltage source, then eliminate your current source. How to eliminate current source? Then it will become open circuit. Now, what is V sub EB? Your V sub EB here is the voltage at this terminal, which is equal to the voltage drop in this R sub 2. So whatever voltage drop here in R sub 2, that is your V sub EB, and that will become your Thevenin voltage later. Okay, so that is just simply equal to V sub EB is just simply equal to the voltage drop across R sub 2. So how to determine this one? Now your V sub EB is equal to, okay, so it seems that this is now series circuit, or we have this loop, okay, Kirchhoff's current law, Kirchhoff's voltage law, okay. So your V sub EB is just simply equal to the current, okay, the current that will flow here times your R sub 2. Okay, so what is this current? What is this current that will flow here? Your current is just simply equal to the voltage divided by the sum of these two. Okay, I hope that you can follow, no? That your current that will flow here at R sub 2 is just simply equal to the voltage source divided by the sum of these two resistances, because they are connected in series. Okay, so we have this one, no? This is equivalent to our current. If this current is multiplied to your R sub 2 here of 2 kilo ohms, we have here, then that will be your voltage drop across here. And the voltage drop across here, I will repeat, this is just equal to this terminal voltage, which this terminal voltage could be the factor of your, to determine your Thevenin voltage. Okay, so if you're going to simplify this one, that is equal to positive 3.75 volts. Okay, another solution, or next thing that you are going to do is you are going to solve your V sub EB, the terminal voltage here, by replacing the source to the current source. So your current source here is 5 milliamperes. Then remove your voltage source. Again, to remove the voltage source, just replace it with this voltage source here will be replaced with the this wire here, so it will be short circuited, no? So what will happen? Okay, as if we are going to analyze the circuit, no? This terminal voltage of V sub EV, then we used 2 here because this is the second solution. This is already second solution where we are going to use our current source. Then that is V sub EV. To determine this one, again, no, it is just the equivalent to the voltage drop across R sub 2. So R sub 2 is, we have here R sub 2 is, or V sub EB is equal to the current here, I sub 2 times R sub 2. Now, what is this current I sub 2? Okay, so as you can see in this circuit now, this if this is our current source, this R1 is parallel with R2. Okay, this R1 is in parallel with R sub 2. So we have two resistances connected in parallel. We have the total current. Then we can make use of the current divider rule, in which in a current divider rule we have the total current. Then if you are going to determine the current in R sub 2, our numerator is the opposite, no? Okay, so this is now the solution. Okay, so this is your total current of 5 milliamperes. Then our numerator is opposite to where we are going to determine our current. So what is the opposite? Resistance. So we have the 6 kilo ohms divided by these two resistances of R1 and R2. Okay, so this is now your I. This is now your I sub 2, no? So this is now your I sub 2, and this is to be multiplied by R sub 2, which is equal to 2 kilo ohms. So that is to solve for B sub EB 2. Or if you're going to simplify this, this is equivalent to positive 7.5 volts. Okay, so to determine the equivalent voltage or the Thevenin voltage, that is the algebraic sum of these two voltages of V sub EB using the voltage source and V sub EB using your current source. So algebraic sum because, for example, if it so happen that our one of the voltage here is negative, then you must have to subtract any of these two. Okay, so therefore, since they are all positive, first solution is positive 3.75 and the second solution is positive 7.5. Okay, take the sum of these two voltages, then it will result to 11.25 volts. Okay, so that is your uh, the Thevenin voltage. Okay, so our equation, we have our new equation now, new circuit now. We have the simplified circuit. You have the Thevenin voltage. This is your Thevenin resistance. Of course, connect back the load resistance here. So, according to the definition of the maximum power transfer, we will be assured that the power transferred in the load is maximum if the load resistance is equal to the Thevenin resistance. And since our Thevenin resistance is 1.5 kilo ohms, therefore our load resistance is 1.5 kilo ohms. So with that, 1.5 kilo ohms. As for the load resistance, to have the maximum power transfer, then the voltage drop here will be uh, the half of the Thevenin voltage source, because they have the same value of 1.5 kilo ohms, 1.5 kilo ohms for R sub L. Therefore, the voltage drop across R sub L is just half of this Thevenin or derived Thevenin voltage. So that is why we have this 11.25 divided by 2, or that is equal to 5.625 volts. Okay, to solve for the load current, if our power is maximum, then we have this, according to Ohm's law, we have this V sub L over R sub L. Your V sub L, the load voltage is 5.625, then divide by R sub L, which is derived from derivation, that is 1.5 kilo ohms, then more or less that is equal to 3.75 milliamperes, our load current. Okay, class, that is the solution using this maximum power transfer theorem. Okay, so we have to determine the power delivered to the load. Now try to check now. So power delivered to the load is equal to V squared over R sub L. That is the modified formula of our power. So V sub L is now 5.625 divided by 1.5 kilo ohms. Quantity squared, then divided by the resistance R sub L of 1.5 kilo ohms. So more or less that is the load power, maximum load power is 21.1 milliwatt. Okay, or you can use this formula of the load power, I sub L squared R sub L, where your I sub L is 3.75 milliamperes quantity squared, your R sub L is 1.5 kilo ohms, so they are just the same, 21.1 milliwatt. Okay, so that ends our chapter 7, applying the conversion of our sources from voltage source to current source, or from current source to voltage sources. Then Melmans Turin, that is to help us simplify voltage sources connected in parallel, and the maximum power transfer theorem, which we are going to solve or assure that the maximum power is delivered to the load. Okay, to determine maximum power transfer, it has to assume that the load resistance is equal to the Thevenin resistance or the Norton resistance. Okay, so that's all. Thank you very much, and continue studying, and God bless us all.
We are one in mission and vision, instilling excellence in electrical profession, having a dynamic professional association, making innovative contributions to